So another major skill that we learned last year in grade 10 that we will definitely need this year is balancing reactions. Now, what is this all about? Well, chemistry is really just like cooking or baking or whatever. It's because we're basically mixing ingredients to create a new product. The ingredients don't disappear, they just kind of combine to form something different, something new. So here's an example. We're making s'mores, so it takes 2 cracker squares, a marshmallow, and 3 chocolate squares to make 1 s'more. So if I want to make 2 s'mores, I'm going to need twice as much of all the ingredients. And the balancing is basically those ratios, that lowest number ratio that we need to make our products. In chemistry, you can also think of like a chemical reaction as like playing with Lego, where you take apart the Lego bricks and you put them back together in a different way, but you use all the same bricks. The bricks don't disappear, they're still there. Just like with our s'more here, the cracker squares, the marshmallow, and the chocolate squares are all there, they're just now all combined. So this is all because of something called the law of conservation of mass, and we'll talk about that in just a second. So a chemical equation is, or a reaction, I guess you can also call it, is something that describes a process in which substances will undergo a change to make something new. We always start with what we call the things that are reacting. We call them reactants, and they are making something called a product. So products are produced, reactants are used. And so if we're talking about, for example, the combustion of propane. So you take propane and you react it with oxygen, and these little elements and atoms, they start to recombine in a different configuration. So you got like hydrogens here and oxygens here making waters, and you got the carbons in here with some oxygens here, and they're making carbon dioxides, and you're getting some heat out of that as well. Well, it doesn't matter if we're talking about the atoms or molecules, the number of things that we start with and the number of things that we end with are the same. So in other words, the mass of all this must be equal to the mass of all of that. We haven't changed the number of oxygens, carbons, or hydrogens. So that's where this balancing comes in. And that's actually why we call it balancing, because if the masses are the same, they would be balanced like a teeter-totter. If you have the same mass on both sides, teeter-totter would be perfectly balanced. So according to that law of conservation of mass, we can't create or destroy matter. Matter is conserved throughout a reaction. So the total number or total mass of our reactants must equal the total mass of our products. And that brings us to balancing. Now in grade 10, you did a bunch of balancing. We're going to hopefully make this a little bit easier, but it's basically balancing comes down to practice. But there are some tricks of the trade that I'll teach you as we go through. So the first thing is you actually have to figure out what's your reactants, what your products, and we're going to set up an equation. So that's kind of our first step. So determine the mass of reactants and products. Or sorry, determine the reactants and products. Sometimes the word problems can make this a little bit tricky. So if we're talking about this example, sodium metal combines with chlorine gas to produce sodium chloride. So in this phrase, sodium metal is combining with chlorine gas. So those two things are what are reacting, and they're producing sodium chloride, which is our product. So here's our reactants, and here's our products. Now, when we start writing our reaction, we have to assemble the equation, put the reactants on the left, we always work from left to right, the products on the right, and we separate it by an arrow, not an equal sign, because they are not equal, they are making. The arrow actually means yields. And it basically means gives way to, or produces, or makes. Now notice the way I wrote the formulas. The formula for sodium is just Na, but the formula for chlorine is Cl2. Now sodium chloride is actually not NaCl2, it's Na plus and Cl minus. It has to go together in a 1-to-1 ratio, so it's just NaCl. So where did that other chlorine go? And that's what I'm kind of saying here is our compounds must be neutral, the elemental gases have to be diatomics, like all of those rules that we did for naming still apply. We can't change the formulas. The formulas are whatever they are. So if I'm reacting sodium with chlorine, making NaCl or sodium chloride, I can't alter their formulas to make the equation balance, but I can alter the number of those things that I have. And that's what balancing is all about. So step 3, Now, I wouldn't probably make this list every single time. As you get better at this, you won't need to. But you can list out the atoms of, or the different atoms you have for reactants and products and make the list the same. So if I'm looking at this reaction, I've got 1 sodium on this side and 2 chlorines on this side. On the other side, I only have 1 sodium and 1 chlorine. So I need 2 times this by 2. I cannot do that though, because now I've changed the equation or the formula for sodium chloride. That is not what sodium chloride is. So what I'm going to do is I'm going to add a coefficient, a big number in front. And that means that I'm going to make 2 molecules of salt, not just 1, which means that now I've multiplied this by 2. But in doing that, now I have 2 of these and 2 of these. So chlorines are good, but the sodiums are not. I can't go back and just do this because you can't change the subscripts. The subscripts are whatever they are, but what I can do is have 2 sodium atoms. So I'm going to double this and makes 2. So now we have 2 of everything on both sides, and our result would be just 2Na plus Cl2 makes 2NaCl. Notice if there's no coefficient, we just understand that there's a 1 there. So there's always a 1 understood here if you don't have a coefficient. So now, when you get to combustion reactions, we balance those in alphabetical order. So if you remember from last year, and we're going to review the different types of reactions next day, but reactions that look like this, where you got a bunch of carbons and hydrogens together, reacting with oxygen, making CO2 and H2O. When you want to balance these, we start off by doing them, or we always do them in alphabetical order. It will always, it'll make your life a lot easier if we do it this way. Basically, one of the major tricks to balancing is to look for the easiest things to balance first. So for me, I would avoid oxygens in this because on one side it's in one place, and on this side it's in 2 places. So when that kind of stuff happens, when you mess around with one coefficient, you mess around with all of them. So it's easier to balance the simpler things first and worry about the more difficult things towards the end. So starting in alphabetical order, I'm going to do carbons first. So there are 3 carbons here, so I'm going to put a 3 there. Now to balance the hydrogens, I have 8 here, so I need 4 times the 2 would give me 8 on the other side. Now I'm going to look at my oxygens. And on this side, I'm going to have 3 times 2, so there's 6 oxygens here, and 4 times 1 is 4 more oxygens there. So that's a total of 10 oxygens on the product side. So to get 10 oxygens on the reactant side, I'm going to put a 5 there. And now my reaction is balanced. So it would be 1, 5, 3, 4. Now, sometimes it gets a little trickier where it doesn't always work out so nicely. But you'll see in a second, if we follow the same strategy, it's not so bad. So starting off with carbons, I'm going to go, we have 2 here, so I'm going to put a 2 in front. Now we have 6 hydrogens, so I need a 3 in front of the water. That gives me 6 hydrogens. So now let's look at our oxygens. So I get 2 times 2 is 4 from the carbon dioxide, and 3 times 1 is 3 from the water. That's a total of 7 oxygens. I can't times something by 2 to make 7. So what I've got to do is double everything, because we don't want decimals or fractions in our balanced equations. We want whole numbers. So what I'm going to do is I'm going to go back and double everything. So I'm going to put a 2 here. The 1 in front of this becomes a 2. This 2 in front of carbon dioxide, I'm going to change that to a 4. And this 3 in front of water becomes a 6. So now what I've done in essence is now I have 8 here and 6 here, so this becomes 14. Well, 2 times 7 is 14. So there's our final balanced reaction. It should look something like that. Another kind of acronym that might help you is to balance. A little strategy is this. Maybe I'll write it this way so it makes more sense. So you write. So M if you can remember the word macho, this might actually help. So you always start with your metals, then your A metals. Now we call them non-metals. Then you go to your carbons, hydrogens, oxygens. If you can remember macho, you can balance any reaction. Now, what does all this mean? Well, on the individual scale, I'll come back to try these ones in a second. On the individual scale, these coefficients are usually talking about atoms or molecules, but because atoms and molecules are so small, we're going to have to end up dealing with huge numbers of them because like 1 atom of sodium is not measurable, or even 2 atoms of sodium for that matter. So this isn't a practical scale because if you have a grain of salt, you're going to have billions of sodium atoms. So we need a much, much bigger scale like moles, and we're going to get back to moles later. So now let's go back to the balancing. Give these a try. Pause the video, give them a try, and then come back and check and see how you did. And as I go through them, I'll maybe talk about some tricks of the trade as I do them. So if we're looking at the first one, right away, I'm going to leave the hydrogens alone because right off the start, I have 2 and 3. I'm just going to leave those alone for now, and I'm going to deal with the nitrogens because to me they just look easier. There's 2 on one side and only 1 on the other, so if I put a 2 here, that fixes the nitrogens. And by doing that, now I have 2 times 3 is 6 hydrogens on the product side, so I'm going to put a 3 there. So there's my reaction is balanced. Now when I'm looking at the next one, again starting with metals, well, I look at manganese, they're balanced, coppers are balanced. The only thing that's not balanced is the chlorines. So if I put a 2 there, that fixes those chlorines, but I need to put a 2 here to fix the coppers that I just messed up. Now, here's where knowing polyatomic ions or complex ions really helps us. So first things first, I'm going to look at the metals. So let's deal with the metals first, starting with bariums are already balanced. Aluminums, though, there's 2 on the reactant side, so I'm going to put a 2 there. Now we're going to look at our A metals or our non-metals. I'm going to leave the SO4s for a second because they just look more complicated. Let's do the chlorines. So 2 times 3 is 6 chlorines. So that means I have to put a 3 in front of barium chloride to get 6 chlorines. So now in doing that, I've messed up my barium, so I'm going to fix those while I'm at it before I forget. So there's my 3 bariums and 3 bariums. Now let's look at sulfates. In grade 10, you probably looked at sulfurs and oxygens separately, but because we know that this whole thing is a sulfate and it stays as a sulfate, let's just look at sulfates. So on this side, you have 3 sulfates here. Well, on this side, there's 1 sulfate in the compound times the 3 from the coefficient. So you have 3 sulfates on either side. So instead of looking at sulfurs and oxygens individually, it's a lot faster to look at sulfates. So when you see polyatomic ions, you can balance them as 1 unit, 1 whole thing. And that makes your life a lot easier than breaking it down into the individual elements. Now, last one is, looks again like a combustion reactions. So we're going to start off with our carbons, then go to hydrogens, and then to oxygens. So let's start off with carbons. So there's 5 there, put a 5 here. Now I need 12 hydrogens, so that means I put a 6 in front of water. Now let's check our oxygens. So 5 times 2 is 10, plus 6 times 1 is 6, so it's 16 oxygens. So I need 8 in front of the O2. And now we're balanced. The only way to get kind of better at this is literally just to do a bunch of balancing. You'll start learning little tricks and tips and just even kind of getting a pattern down or kind of a strategy down to balancing. And it basically ends up coming down to sometimes even just guessing and checking and seeing if you get your answers right. But some of the tips I showed or explained might actually make that process a little bit easier.